All right, this is lecture 2 of Calculus 1 at Bethel University in fall 2019. We're going to start content today, and I would highly recommend taking notes, as I see many of you have your notebooks out. There will be a lot of content, so you might need to just paraphrase sometimes. You might not catch everything if you try to write down every word. But I would try to at least write down every equation that you see. I think personally, this is my personal theory, I think that writing things down in class, writing things like function notation, f of x, helps you to not get stuck on exams, believe it or not. Now, of course, doing well on exams implies doing more than just writing down symbols. You need to understand problems and how to solve problems, but sometimes I think people maybe could do better if they got more used to writing things, because there's sort of like this freeze you experience sometimes during exams, anxiety, and you don't know what to write, okay? If you practice writing things down in class nicely and also in your homework nicely, that will help you develop, I think, brain connections to do better on exams and quizzes. So we're breaking this lecture into 2 parts, about a half hour for each part or so. Lecture 2A, I'm calling on direct proportionalities. And lecture 2B, linear functions in general. Direct proportionalities, the way we typically think about them, are actually linear functions too. All right? Okay, so that's why I added the in general part. At the beginning here, let's talk about why are linear functions important. Where are we going? Well, the first thing to realize is they are simple. Okay? That's the first thing to keep in mind about linear functions. Compared to other functions, at least, they are simple. In mathematical modeling, when you're using math to try to solve applied problems, there's an important mantra to keep in mind, and that is this. Keep things as simple as you can while maintaining reasonable accuracy. Or, maybe in a funny way, keep things as simple as you can get away with. Okay? Now, in this class, you should do what I tell you, but when you're trying to apply math in your life, outside of the classroom, keep things as simple as you can get away with. Yeah. Meaning you maintain reasonable accuracy. And you always have to test your model against reality. Is my mathematical model that I constructed in this computer program that I made, is it matching our data, for example? Is it reasonably accurate? And if it's reasonably accurate, you often go ahead and use it. Okay? But then you want to keep monitor it and see, is it continuing to be accurate? Because things can change over time. Their formulas and graphs are simple. Their formulas involve the variable to the first power. That's as simple as you can get. Okay? And their graphs are simple, just straight lines. That's as simple as you can get. Straight lines. They're relatively easy to work with algebraically. You don't need things like the quadratic formula for linear functions. We will use the quadratic formula, but you don't need it for linear functions. You can solve for x typically in a pretty simple way, and find an exact answer. It's typically unique, unless you're talking about systems of equations where sometimes you have infinitely many solutions. But that's not what we're doing here. And they can be used to approximate, this is part of the purpose, the importance, they can be used to approximate functions that are not so simple. Nonlinear functions. Okay, any function that's not a linear function is called a nonlinear function. Especially, this is a little bit more mysterious term, transcendental ones. What do I mean by that? You've heard of transcendental meditation? Okay, that's not what this is. Transcendental, they are, sort of think of it this way, they are kind of mysterious in a way. Things like e to the x and sine x and cosine x, technically those are kind of mysterious functions, right? You plug in values for x, simple values like 1, for example, and you typically get irrational outputs. What are irrational outputs? Well, they're not rational. A quick summary of irrational numbers is they're not fractions that can be written as ratios of whole numbers, integers. Their decimal expansions typically go on forever without a repeating pattern, though they can actually have patterns, just not repeating patterns. Those are irrational numbers, but so these functions are mysterious in some way because of that. That's why we call them transcendental ones. This is actually one of the main purposes of calculus overall, is to approximate these nonlinear and transcendental functions. That is one of the main purposes of calculus. And we will talk about that purpose later in the semester. Okay, so keep that in mind. That's why linear functions are important. They're simple and they're useful. That's a quick way to say why they're important. Simple and useful. All right, so again, lecture 2A, the main content is direct proportionalities. This is a simple but extremely important situation where linear functions arise. A use of linear functions, a special kind of linear function. Here's a common situation. Unit conversions. I'm going to need my calculator here. It is a good idea to typically bring your calculator to class and have it out so you can check work with me. I might try to see if I can get a calculator emulator on this computer, though I was having trouble getting one on a different computer here earlier this week. Hopefully that won't be a problem. For example, converting feet to meters, okay? Here in the US we use feet, but everybody else in the whole world uses meters. In science classes you should use meters. But we want to convert. What's the conversion factor? It's approximately 0.3048 meters per foot. So, if, for example, you wanted to figure out how many meters tall a basketball player is when you know they are 7 feet tall, you just multiply by the conversion factor. So you would do 0.3048 times, let's go ahead and let's put the unit there though, meters per foot, which you can write like this, times 7 feet. The feet cancel, leaving you an answer in meters. That is the product of those two numbers. And if you use your calculator, 0.3048 times 7 is about, well, it's 2.1336 meters. Let's say approximately 2.13 meters. There are issues to think about in some of these things with like significant digits and that kind of thing. At the moment, I don't want to talk about that. Okay, so I'm just going to go ahead and be satisfied approximating this to say 2 places after the decimal. This conversion factor is an approximation as well, so definitely the answer is approximate. Okay, you've probably all done that, I hope, in science classes, whether here right now or in the past. Unit conversions. There is a corresponding, I'm going to go ahead and call it a proportionality equation based on this. Typically, we will do the standard thing and use letters for variables, x and y, for example. But sometimes, like right now, we might use words for variables. For example, I could write meters is equal to, really approximately equal to, 0.3048 times feet. So there I'm using entire words to represent variables. That's okay. Sometimes people do that to really emphasize the meaning of the variables. We won't typically do this. It's an equation. This is your dependent variable. And this, the feet, is your independent variable. Moreover, not only is it an equation, we can think of it as an equation that defines a function. We can think of this output as being the output of some function. Here I'll go ahead and be standard. Use the letter f to represent the function. Name. F of feet. So f is the function name. Function name. And when you see this symbolism, you should think of this entire expression as representing the output of the function, a number, when the input is some number, whatever you're talking about. In the case of this basketball player, it would be, say, 7. The output, the whole thing of the function. You say, and this is really important, you say f of feet, which sounds really weird, but that's what you say if your variable name is feet. This is f of feet. Usually you say something like f of x, right? Because usually your variable is x. It's not f times feet. Okay, that's important to realize. Some people get confused and think it's f times feet. No, it's f of feet. F is not a number, it's a function name. Feet is a number. The whole symbol represents a number. F of feet is a number, but f itself is not. Subtle conceptual details that cause confusion, but you want to work at making them not be confusing, okay? Can we graph it? What's the graph of the corresponding function? Sure. We can plot points. We can make a table with the feet values here and the meters values here, or call them x and y if you prefer. That would certainly save time. And plug in numbers. Plug in numbers of feet into the function. I'll go ahead and keep it simple. 0, 1, 2, 3, 4, though I can plug in other numbers too. What's f of 0? Multiply 0.304 times 0 to get 0. F of 1, multiply 0.3048 times 1. We use the formula to find the output to get 0.3048. F of 2, use the formula, plug in 2 in place of feet. So you need to multiply 0.3048 times 2. 0.3048 times 2, that would be 0.6096. F of 3, 0.3048 times 3, and I better use my calculator so I don't make mistakes in front of everybody on YouTube. 0.3048 times 3, 0.9144. And f of 4 would be 0.3048 times 4. By the way, I do make mistakes sometimes typing things in my calculator, so this is again a reason you should be checking things on your calculator so you catch my mistakes, okay? Because I do probably average 1 or 2 mistakes per class period. Okay? Pay attention and try to catch my mistakes if nothing else. Then you can plot these points. Make a graph. I'm only doing positive or non-negative feet because that's what only makes sense here as far as heights of people. You could plot this for negative feet, technically speaking, which could have applications if you're talking about going underground, for example, right? Think of the ground level as 0 height in feet, and you can go underground and think of it as a negative height. Negative numbers are useful. Plot the points. And I'm only going to plot them approximately. Typically, you should try to be a bit more careful than I'm going to be here, but there's the point whose coordinates are 1.3048. I forgot about 0, 0 right there. That's important. Then feet is 2, meters is 0.6096 would be right about here. 3, 0.9144 would be right about here. And finally 4, 1.2192 would be right about here, say. Got a bunch of points, what do? Go ahead and say it. Draw a line, connect the dots. Yeah? Wait, do we know for sure it's a straight line? Well, yeah, because your teacher told you it was. And if you plot more and more points, it certainly would look like it's a straight line. That's not a proof it's a straight line. And we're not going to prove it's a straight line at the moment. I'm just telling you it is straight. Okay? The scales on the axes are a bit different. Not too far different from each other, but a little different. Sometimes they are vastly different. That'll come up in this next example. Converting kilowatt-hours to joules. Has any of your parents ever said, oh, we used 1,000 kilowatt-hours of electricity last month? That would be a strange thing for a parent to say. I think maybe I've said it for my kids, or at least my wife. We used 900 kilowatt-hours of electricity last month. That's actually a pretty typical amount of energy to use in a month. somewhere in the ballpark of a little less than 1,000 kilowatt hours. What is kilowatt hours? It's just a measure of energy. 1 kilowatt hour is a relatively large amount of energy. Joules is the more standard scientific unit of energy. 1 joule, though, is a relatively small amount of energy. What's the conversion factor? 3.6 times 10 to the 6 joules per kilowatt hour. 3.6 million joules per kilowatt hour. Yeah, that's a big conversion factor. Let me go ahead and use y and x just to be quicker here. The conversion equation would be y equals f of x equals 3.6 times 10 to the 10 to the 6. I'll go ahead and write that as 3,600,000. And now you could use that conversion equation, that proportionality equation, as a function, if you like, to convert 867 kilowatt hours to joules. F of 867 is 3,600,000 times 867. It's over 1 billion joules. Looks like if I'm counting the number of zeros correctly, it's 3,121,200,000 joules. Okay, so yeah, if a house consumes in a month 867 kilowatt hours of energy, this is how many joules they consume. A lot of joules. But that's because a joule is a small amount of energy. And we could graph this function as well, though obviously you want to use different scales on your axes. You know, if we were graphing, maybe doing something like this, 10 joules, then 20 joules, then 30 joules. For example, when x is 10, y would be 36 million. That would be 36 million here. 3.6 times 10 to the 7th is what that, I'm writing there if you can't quite see it. 3.6 times 10 to the 7th would be the first point, and then you plot a bunch of other points, and yes, once again, you get a straight line through the origin. Okay? By the way, I'm not going to do it here, but these things have inverse functions. You can go reverse, right? You can go from, instead of going feet to meters, you could go meters back to feet. Instead of going joules to kilowatt hours, you can go kilowatt hours back to joules. You can divide both sides of this equation by 3.6 million. You get x as a function of y. That's just all I'll say about inverse functions for today, though.
I have a question.
Mm-hmm.
So that would change the independent and dependent variables?
Yep, it would change which variables independent and which variables dependent. Yep. Okay, and if your variables mean something, here's something to keep in mind. If your variables mean something like they do here, do not swap them. Right? That would be more clear if I, instead of x, I had used J for joules, and if I had used kWh for kilowatt hours there. If I solve for J in terms of kWh, don't swap the variables like your teacher may have told you in the past, because that would change the meaning. You're going to get all messed up. So if your variables mean something when you solve for an inverse function, do not swap the variables. That's done for other reasons, usually. I'll talk about that in a later lecture. All right, let's talk direct proportionalities and functions in general. I'm going to go pretty quickly here. The formula is this. In general, y equals f of x equals k times x. You see the dot there, but usually we don't bother putting the dot when there are just letters. We usually write kx, and it's understood here that both k and x are numbers, and I multiply. As opposed to meters and feet, where those letters all went together to form one variable. I'm not, when I write the word feet, I'm not saying f times e times t. In that situation, the whole symbol represented the variable. Here, two separate numbers, k and x, are getting multiplied. The number k is called the constant proportionality. A couple fundamental properties about direct proportionalities. Fundamental property number one, multiplying the input by a given factor factor, means multiply, that also multiplies the output by the same factor. So for example, if you multiply the input by 2, the output gets multiplied by 2. If the input doubles, the output doubles. If you multiply the input by 3, tripling the input, if the input triples, the output triples. If you multiply the input by a half, cutting it in half, so to speak, you multiply the output by a half as well. It gets cut in half too. But this works for any multiple. You can multiply the input by 2.695. The output gets multiplied by 2.695. Here's a way to prove this. Write this line here. If y equals f of x equals kx, that's a direct proportionality. How do you prove this doubling, tripling, etc. fact? Let a be your arbitrary factor. I'm multiplying the input x by a. Okay? This is really important to keep in mind conceptually what's going on here. When you see ax here, I am multiplying the input x by a number a. A could be 2, a could be 3, it could be a half. It could even be negative. It could even be pi. It would be weird, but it could be pi. What do? Simplify this, and then think. We need to find f of ax. What is the function notation imply to do? This is something you've learned in the past, but may have forgotten. Wherever you see the variable name, in this case, x right there, replace x with whatever's inside the parentheses there. So instead of taking k times x, I get k times ax. Notice the similarity between these two symbols right here and here. Oh, off the board there. The similarity between this and this, I won't write on the wall. Between that and that. They look very similar, but they mean different things. They're related, obviously. This is f of ax. This is k times ax. Keep in mind what the symbols represent. F is a function name. It's not a number. K is a number. A is a number. X is a number. This is a multiplication. There are properties about multiplication. For example, you can move numbers around when you're multiplying them all. That's called the commutative property because they're commuting back and forth. You can put parentheses in different spots. I kind of did both things in going from here to here. I switched the A and the K around. Technically, I probably should have proved that more carefully. I would have done something like this. K times AX is KA times X. That's the associative property. Is AK times X. That's the commutative property. And then the associative property, we'd write it like this. Okay, if I wanted to verify every single step of that, that seems like overkill. And I suppose for Calculus 1, it is kind of overkill for us. Okay. You can definitely do this when you multiply numbers. But what's kx? It's the output of the original function at the input x. You can replace kx, well, with y if you like, or with f of x. I could have just jumped from here to here. I could have skipped that step. Then what does it mean? What role is this about? This is saying if I multiply the input by a, the output gets multiplied by a. If I double the input, if a is 2, I double the output, 2 times f of x. If I triple the input, if a is 3, I triple the output, 3 times f of x. If I cut the input in half, if a is 1/2, then the output gets cut in half, if a is 1/2. Okay? Fundamental property 2. K is the rate of change of y with respect to x. It's also called the slope of the graph of the function. You've heard these words before. What do they mean? Well, here's what it means symbolically. We'll also look at what it means graphically shortly. If the change in x is delta x, okay, you've seen this kind of thing in science classes before, maybe some math classes. Delta variable name is one quantity that people typically use to represent the change in the quantity. So this is not delta times x. This is one variable named delta x. If that's the change in x, that's common notation to use. What is the change in y? Let's do it on the board before we see it on the PowerPoint. What is delta y, the change in y? What does it mean for x to change by delta x? It means it becomes another number, so to speak, at least in your imagination. It becomes x plus delta x. That's taking the input, original input x, and changing it to another number, x plus delta x. Changing x by delta x. There's the picture when delta x is positive, but delta x could be negative. You see delta x is positive. If delta x is negative, then the change in x looks like this. You'd still write a plus sign there, though, because when you add a negative number, it becomes smaller. It's like a subtraction of a positive number, right? Adding 2 is the same as subtracting, or adding negative 2 is the same as subtracting 2. So you write a plus there, but because delta x is negative, this would be smaller than that. What do I do here? Just use the formula for f. Remember, no matter what is in here, go to the formula for f. Right at the top there, replace x with this whole thing. So I need to take k times the whole thing. Once again, we have two similar looking things here, but conceptually they're different. This is f of x plus delta x. This is k times x plus delta x. F is a function, and k is a number. The distributive property, then, is a property that you can use to bring the k through the parentheses here. Might be a good idea to put a dot there. You don't have to, but maybe it's a good idea. Emphasizing multiplying these two numbers. Again, delta itself is not a number. X is a number there, but delta x is the entire number right there. Oops, I made a mistake. I forgot to subtract after that too. Okay? That's the change in y. The difference in the function values.
Why would you subtract f of x?
Because you want to find the change in y, not just y itself.
Oh, okay.
Here is f of x. Here is f of x plus delta x. I want to find the change in the value, the output here. That's the distance between these things. I need to subtract. Right, 7 minus 2 is 5 is the distance between 2 and 7 on the number. I forgot to do that, probably. That was a bad mistake. Cancel the kx's, you're left with k times delta x. That's what this next line of PowerPoint will show. And how do you find the slope? Rise or run, change in y over change in x. And the delta x is canceled, giving you k. As long as the run is non-zero. As long as x is actually changing. This equation is important, right? How to calculate the slope. This equation up here is actually important, that delta y equals k times delta x. That's important for interpreting k as a rate of change, which we'll talk about more later. Getting close to a half hour here. I think I'm going to go a little over a half hour for this first half of the lecture, and we'll be a little less than a half hour for the second. Here's some visuals. property one, what was property one again? Double the input, you double the output. Triple the input, you triple the output. Cut the input in half, you cut the output in half. That's property one. And this is the way to visualize it. The original input x is at 2 there. A is the factor you're multiplying x by. When it pauses, A is at 2, you can see. That's doubling the input. 3x is the output, because the function is f of x equals 3x. A is 3. When you double the input, like right now, you double the output. Right now. When you triple the input, like right now, you triple the output. When you cut the input in half, like right now, you cut the output in half. I wish I could make this go slower, but I really can't. It's sort of set on a certain speed. This is a graphical illustration of that property. Property 2, when the change in x is delta x, the change in y is k times delta x. So the slope, rise or run, stays constant. In this picture, this triangle representing the length of this side is the rise, the length of this side is the run. This triangle is always the same shape, it just gets bigger and smaller. All those triangles are similar to each other. The ratio of the sides, this side divided by that side, delta y divided by delta x, stays constant. I will try to make these PowerPoints available to you too. I think I can put them in like a Google folder and just share them. They only play though if you put it in the presenter mode. If it's just in the static mode, you won't see them animated. More examples, and then we'll take a break. Distance traveled is directly proportional to both speed and time of travel. Distance equals rate times time. D equals RT. Which one of those quantities is the independent variable, R or T? Well, either one could be. It depends on the situation. If you know the rate, 70 miles per hour, but you don't know T, then T would be the variable. If you know the amount of time, say 3 hours, but you don't know the rate, R, then R would be the variable. Which one's the variable, which one's the constant, depends on the situation. Simple interest is directly proportional to 3 quantities. The principal, which is the amount you deposit, the interest rate, which is just whatever they quote you for their interest rate, and the amount of time of the investment. I equals PRT is a common way to write that. I is the amount of interest that you earn. It's a dollar amount, say, or a euro amount. P is a dollar amount, a money amount. Principal, how much you deposit. R is the interest rate. If it's, say, 2%, R would be 0.02. And T is the amount of time. Typically, R is a percent per year, say 2% per year, so T would be an amount of time in years. If R was a percent per month, then T would have to be the amount of time in months. You don't really earn simple interest on your bank account except during each individual quarter. When you combine all the quarters together, then you earn what's called compound interest, which we'll talk about maybe some on Friday. Direct proportionalities actually can be a little bit more general and lead to nonlinear functions. They can be proportional to squares, cubes, etc. of the independent variable. For example, the area of a circle is directly proportional to the square of its radius. I equals pi r squared. A is some constant times r squared. The constant is pi, like we talked about in lecture 1. Here's a physics one. The magnitude of the gravitational force on a mass by another mass is directly proportional to the distance between them raised to the -2 power. Whoa. F equals kr to the -2, where F is the force magnitude and r is the distance between them. That's a mouthful, but it's something that's true. That's one of that's Newton's law of universal gravitation. What is K? Well, K is kind of mysterious at the moment. It actually depends on what the masses are themselves, for one thing. Okay? All right, let's take a break.